In this chapter, we will look at the variables in wheels to be tested, an overview of component options, wheel specifications, how measurements will be taken, and then the testing apparatus. With data from testing, I found some concluding facts profound. The next 4 sections will urge introspections, and the final one will astound. First, we'll talk about the testing protocol. Our components are mostly velocity race hubs and velocity rims, Sapim spokes, and Sapim nipples. I also have later on some nice rims from Knox Composites in Knoxville, Tennessee. On the left, you see a sample of a wheel. We're looking at the wheel on the drive side, and we have to have a way of referring to the positions of the spokes. Starting at the top of the wheel, which we will consider to be 0 degrees, then we can label every spoke every 30 degrees. Velocity was the sponsor for most of the experiments that we're doing with wheels, and I'm using the velocity race hubs for all of the wheels that we're going to experiment with. Many of them are also built with the Velocity Deep V rim, which is a very strong, venerable rim, and this is the extrusion. Another sponsor was Sapim that made available to me a wide variety of spokes and nipples. And there's a lot to choose from. We're going to look at straight gauge spokes, butted spokes, double butted spokes, and arrow spokes and see what's available. First, the straight gauge leader spoke. It comes in 5 different actual diameters: a 1.8 millimeter, a 2, a 2.3, a 2.6, and a 2.9. The most popular of these is the straight gauge 2 millimeter spoke. This is the butted spoke. It's called the strong, 2.3 millimeters at the elbow, and then the rest of the spoke is 2 millimeters. Then there are 5 spokes that are double butted, starting with the force, which is actually a triple butted spoke. And I'm not going to read all these numbers because you can see them. Starting with the force, then we have the race, the D-light, laser, and super spoke. Under arrow, we have the very well-known C-X-ray spoke and the less-known CX. Now I'm going to give you the mass in grams of one spoke of each type at 260 millimeters starting on the left. Let's focus on the C-X-ray for a minute. You could look up this description on the website for Sapim. Here are some technical specifications, and there's the weight I mentioned to you a minute ago. This is the type of stainless steel that's used in the spokes: 74% iron, 18% chromium, and 8% nickel. This is known in the industry as 18 and 8. This line shows us the strength in the middle section, 1,600 newtons per square millimeter, and from that information I can calculate the tensile strength of the spoke. I need to calculate the cross-sectional area of the elliptical arrow part of the spoke. Here's my ellipse, and the dimensions that Sapim gives me tells me that I have a major axis of 2.2 millimeters and a minor axis of 0.9 millimeters. That gives me these half distances. Side A or line A is 1.1 millimeters, B is 0.45 millimeters. This is the formula for the area of an ellipse, and when I calculate that out, I get 1.55 square millimeters. So my tensile strength is 1,600 newtons per square millimeter times 1.55 square millimeters. That gives me 2,480 newtons, which is about 546 pounds. So if I imagine that I have a ceiling and I have a spoke, a CX-ray spoke attached to the ceiling, then I could hang from that spoke a barbell of 546 pounds, and that is the tensile strength of the spoke. I've known about the tensile strength of this spoke for a long time, which led me a few years ago to perform the Sapim CX-ray death-defying demonstration. Here is a furniture dolly on which is mounted a bucket filled with 300 pounds of dirt and rocks, and I've hooked up a block and tackle to it. The block and tackle is attached to the ceiling and is all supported by a single Sapim CX-ray spoke. After hoisting the weight up, here I am relaxing under the load and then reading the Park Big Blue Book of Bicycle Repair. And these two photos were taken nervously by my wife, who realized if the spoke broke, I would be crushed to death right in front of her. But my wife, after seeing that I survived the experiment, allowed me to put this priceless family heirloom directly under the load. While we're on the topic of the CX-ray spoke, I want to just give you a peek into something that we'll discuss in much greater detail in the chapter on aerodynamics, but just let me put this seed of thought into your mind that the elliptical shape is very favorable from a standpoint of aerodynamics, and sometimes other spokes are referred to as bladed spokes, but bladed can sometimes mean rectangular like this in cross-section, and that is quite different and not nearly as advantageous as the more airfoil shape CX-ray spoke. The CX-ray spoke can also be made with a number of options, as you see at the bottom. Out of all of those spokes available, the ones that I'm going to use in my experiments are the straight gauge 2mm leader spoke and then the double-butted race and laser spokes. These are the variables in the wheels that we will study: the rim extrusion, the hole drilling, lacing pattern, spoke thickness, and spoke tension. There are 11 different test wheels using these variables, one of which actually has a carbon fiber composite material in the rim. This will be wheel number 1. The choices are going to be to use a Velocity Deep V rim, 24 holes, and radial lacing. Radial lacing is what I will use for many wheels because with radial lacing, the spokes are pretty well isolated and it makes a good model for studying the changes of tension in the wheel. Here we see the 12 radial spokes on the drive side, which is the load carrying side to a great extent. And here we have 12 on the non-drive side. We have to have, obviously, the non-drive side as well, but I'm going to focus my attention on measuring the drive side. So let's disregard the 12 that are on the non-drive side. We'll have, to start with, straight gauge spokes, 2mm, that's the leader, and 80 kilograms of force, or 784 newtons, which I think is about the minimum that you can have to have a reasonably stable and strong wheel. Wheel 2 will be the same, except we will use Sapim race spokes, which are 2mm thick at the ends and narrowed down to 1.8mm in the long midsection. And wheel 3 will be once again the same, except here we will have Sapim laser spokes, which are 2mm thick at the ends and 1.5mm in the long midsection. Wheel 4 will be the same as wheel 1, except we will raise the tension on the drive side spokes up to 130 kilograms of force, or 1,274 newtons. Wheel 5 is like wheel 2, except at higher tension. And wheel 6 is like wheel 3, except once again at the higher tension. Then we'll start looking at some wheels that have a crossing pattern. This will be wheel 7 using the variables and choices shown on the right. Now looking at this wheel, I have labeled for clarity the black spokes are the pulling spokes and the orange spokes are the pushing spokes. And we're going to look closely at this section right here. Here's our expanded view. If we look at this spoke here, this orange spoke, we see that it crosses two black ones. It crosses over this black spoke and under this black spoke. And the spoke next to it, similar situation. Looking at this spoke here, it crosses over this one and under this one. At the first crossing, the orange spoke is above the black spoke and they do not make contact. At this crossing here, the orange spoke tries to push the black spoke out of the screen. The black one tries to push the orange one into the screen. As a consequence of that, changes in either of those spokes will be dampened a little bit by the force put on it by the adjacent one. We don't actually know yet if that's true, but it seems reasonable, so we can form that hypothesis. So I'm interested in learning how much that spoke will be dampened and the variation in the tension narrowed in a crossing pattern compared to the same situation with radial spoking. Wheel 8 is like wheel 7, except here we're going to use a velocity fusion rim and see how the fusion with that extrusion there compares, if any difference, to the deep V. Both of these rims have the same width of an outside width of 19 millimeters and a depth of, in the case of the deep V, 30 millimeters and the fusion 25 millimeters. In wheel 9, we're back to the deep V, but now we're going to use 32 holes and a 3-cross on both sides. Wheel 10 is again the fusion rim, 32 holes, 3-cross on both sides. Wheel 11 is going to use a rim made out of carbon fiber by Knox Composites. It's going to be 32 holes and 3-cross, and the model of rim is a Teocalli 29. This is my most accurate tensiometer, and it's calibrated specifically for Supeme spokes, and I used it over 4,000 times in making the measurements that you'll see coming up. This is the apparatus all set up in my test lab, and I'm going to walk you through this and show you how it works. The table itself is made up of a massive amount of extruded aluminum, all braced and connected together for support. Special connectors effectively attach the pieces together, but are easily loosened so that the apparatus can be dismantled and moved if necessary. The table itself is supported by 8 feet, 4 massive ones in the intersection, which is supporting the bulk of the weight, and then 4 more on the outer corners. All 8 of these are adjustable so that the table can be perfectly leveled. This is Carlos Alfaro, a friend of mine and a computer scientist. He developed a spreadsheet and recorded all the data as I read it off. One of several thousand readings taken here by me and recorded by Carlos. I want to use my movie camera to show you this apparatus because it's turned out to be a perfect setup for measuring spoke tension. The wheel, as you can see, is resting on a treadmill, so I can change the position of the wheel by rotating the wheel by just turning the pulley here on the treadmill, and I don't have to do anything. I don't have to lift up the wheel at all. So this has proved to be very, very useful to be able to position the wheel exactly without having to change anything else. I installed an external cup on the bottom bracket shell, which allows a 3/4 inch threaded rod to go through the bottom bracket, and turned out to be a very good fit. Spaced equally on both sides are some pretty heavy chains that go around the treadmill and through that hole in the table. Right now these chains are slack, which means there's no load applied to the wheel of the bike. But as I lower this jack, which is supporting the weight, then we see that the weight is slowly transferred to the wheel, and at some point the swing is just swinging freely, which means that all of the weight has been transferred to the bike. I now have a 240-pound load on the bike. Of that 240 pounds, about 153 pounds, or about 2/3 of the total, is on the rear wheel. Even with that full 240 pounds applied to the bottom bracket through these chains, I can still rotate the wheel quite easily with the pulley without having to take the weight off the wheel every time I want to move the position of it. To perform tests on a different wheel, all I have to do is raise the jack, switch the wheels, and then lower the weights again. And here's how we'll do the actual tension measurements. We'll take an unloaded wheel, and in this case here, this happens to be a 24-spoke wheel, so we're looking at the 12 spokes on the drive side, and at every 30 degrees there is a spoke, and we will measure the tension of each of those 12 spokes and calculate an average. Then we will put the wheel under a vertical load and once again measure the tension of each spoke at each 30-degree point. Then using the treadmill, we'll rotate the wheel 30 degrees and measure every spoke in the loaded wheel again. Rotate another 30 degrees and measure again. And again. Until I get back to where I started, so that by this time I will have an average tension at each of those 30-degree points, representing the average of 12 different measurements every 30 degrees. And by doing that, I am averaging out any possible inconsistencies that I get in my tension measurements. And that should give me some good data. I'm not worried about the consistency of the tension of the unloaded wheel, because I can do that on the truing stand and make sure that by balancing out the tension carefully that all of those spokes on the drive side are at exactly the same starting tension.